Our next talk is Stefanie Justice on risk reduction through early software prototyping for the Mars Ascent vehicle. Stefanie's from NASA Marshall. Stefanie, are you with us?
I am here. Can you hear and see me?
Yes, great. It's all yours.
All right, good afternoon. As Chris said, I'm Stefanie Justice. I'm the flight software lead for the Mars Ascent vehicle, and I'm from NASA Marshall Space Flight Center. Next chart, please. And just to give you a little overview of what I'll be talking about today, I'll give a brief overview of the Mars sample return mission and MAV's piece in that mission. A little bit of context about where we are, our software development approach, and some of the activities we've been doing over the last couple of years, and how we see that as reducing risk. Next chart, please. So I'm sure most folks by now are familiar with the Mars sample return mission. I know it's been talked about for many, many years, and we're excited to see it becoming a reality before our eyes. As you'll see on the chart, the Mars 2020 lander or rover that we've heard about earlier, that's the first critical piece. Mars 2020 will actually collect the samples of Martian soil and atmosphere and deposit those on the surface of Mars. The next pieces of that mission are the Earth Return Orbiter and the Sample Retrieval Lander. Those can launch in either direction. We are actually part of the Sample Retrieval Lander. So the MAV, Mars Ascent vehicle, will ride up as a payload on the lander. And our job is short and simple, but complex all at the same time. We hold the orbiting sample container, which the Martian samples will be inserted into, and our job is to get those samples into orbit so that the Earth Return Orbiter can retrieve them and bring them back to Earth for study. Next chart. Sounds simple, right? Okay, next chart, please. Just a high-level mission operations overview. We will launch via a vector launch, the first stage to burnout, and we will coast where the MPA, which is the portion of the vehicle that's containing the Oz or orbiting sample, the fairing will separate. The first stage will separate, and then we'll go into a high-speed spin motor burn. And the second stage is actually an unguided second stage. So it'll have some spin motors that'll despin until we reach the Oz payload delivery at our target orbit. And that's where we will release the Oz and enable a beacon to be able to tell the Earth Return Orbiter where we're located. Next chart, please. Some high-level vehicle architecture. As I said before, the Mars Ascent vehicle is part of the Mars Ascent system. It's a two-stage guided, unguided, solid motor vehicle with a pyrotechnic stage separation, electromechanical TVC on the first stage, 2 spin motors and 2 D-spin motors on the second stage, and a monopropellant reaction control system. The MAV payload assembly has an ejectable fairing and contains the orbiting sample. So that's the important piece of the mission that we want to get back. The entire MAV vehicle is approximately 2.8 meters long and 50 centimeters wide. So you'll see, I believe the person on the left is about 6 feet tall for reference. So you'll see that it's a little taller than a fairly decent sized human being. So we're not talking about an SLS size rocket. We're talking about a fairly small rocket, which makes the mission a little more interesting with those constraints. Next chart, please. Some of the mission design constraints that we're dealing with. It's unique. It's first of its kind mission. We've been talking about doing Mars sample return. It's been studied for, as I understand it, 30, 40, 50 years. And I think this is the first point that we've made it to this point in the design process. Because of the size of the Mars Ascent vehicle, we're very mass and power constrained, which also constrains our computing power and resources. So we're very limited on what types of flight computers we can fly on a rocket this small. In addition, the Mars sample return mission is a planetary mission. So we have very strict development schedules. It's not like a mission where you have many launch windows where you shuttle mission where you can just slip to the next available one. There are a couple of really decent windows, and beyond that, you're kind of out of luck. So that provides us immense schedule pressure. Again, we operate as a payload to the sample return lander. So that's kind of a unique position because we are both a vehicle, a launch vehicle, and a payload. And as such, all of those constraints put together, we really have to balance the technical capability with meeting our schedule. So we really have to think about what's good enough, not perfect. We can't design a Corvette or a Maserati if a Honda Civic will do the job. We really just need to meet that mission goal of getting our payload into orbit. And so tailoring and efficient engineering processes are very necessary. The Mars sample return mission is a joint mission. It's managed out of JPL, but the Mars Ascent vehicle portion is managed out of NASA Marshall. So collaboration across the agency and then risk reduction are all keys to success. Next chart, please. So we'll dive into a little talk about the MAV flight software and where we are. You'll see the typical NASA project lifecycle on your screen. We're now at the very beginning of phase A. We're working towards system requirements review, and we just got approved for formulation back in December. A normal software development for the projects that I've worked and from talking to some colleagues at Marshall, software development typically starts during phase A. We need enough lead time before SRR to begin developing software requirements, but we typically don't come in much before that. In this particular instance, we were able to actually start our software development and have software development participation on the MAV team back before pre-phase A when the concept studies were going on. So this is very unique. We called this pre-phase A. So we actually had a Marshall Technology Innovation Program proposal that was awarded for this work so that we could do a couple of different things. One was assess the CFS framework for feasibility on this type of mission. And then it also allowed our team to come up to speed on both the mission and the CFS framework. Those were both areas that we wanted to gain some additional capability in our group. And so this was our way of doing that. In doing that, we were able to participate in the preliminary architecture assessment for the MAV vehicle, where we went through various concept studies and various configurations of the vehicle. And we were able to provide some software focused considerations and develop some high level architecture, software architecture definition for those trade studies very early on. And so in doing that, when we transitioned to phase A for the Mars sample return, we actually had a working prototype for the Mars Ascent vehicle flight software. I won't say it's a complete prototype, and I won't say that everything that we've done is set in stone and will continue, but we do have a working prototype. So that was an exciting achievement for us. Next slide, please. Just a very high level software notional architecture. Again, we're planning to use the core flight system architecture. We were able in pre-phase A to do some trade studies and look at the feasibility of doing that. And we do feel like that's a good option for us given the constraints of the development schedule. We feel like having that reusable framework will be beneficial. And we've also been able, as I'll talk about in future charts, to do some testing on some of the candidate hardware so that we can actually assess performance early on. And so our mission specific layer will be where we focus our MAV development. And those are very typical components like our IMU, our propulsion systems, some drivers for the specific flight computer that we plan to work with, and an interface to the sample return lander. Next slide, please. So I wanted to talk a little bit about our MAV software development approach. We felt like this was something that allowed us to reduce risk from the beginning. Because we came in so early, we could have really adopted more of a wild west approach to software development, because coming in at pre-phase A, we don't have a lot of requirements. We're working from ground rules and assumptions. Those are changing rapidly. But we decided that we wanted to go ahead and adopt our Agile Scrum process from day one. So what that allowed us to do, our organization typically uses what we call a modified Agile Scrum process for all of our projects. But by getting started with that from the beginning, that's been able to morph and change over time so that we could just improve as we go. Where we are today, we're running either 2 to 4 week sprints. Again, we tried 2 week. We're working towards 4 weeks, as we see that makes more sense as we're going into more formal development cycles. We do tag ups 4 days a week, currently via Teams, since we're all virtual, with one via email on Fridays. That allows for folks who are on alternative work schedules, and it supports our NASA Quiet Fridays so that we don't have a meeting on that Friday. But it also gives the team an opportunity to check in. We do bi-weekly retrospectives and planning, and again, that'll coincide with the end of the sprint. So if that's a 4 week sprint, it'll be once a month. And we're working towards monthly sprint reviews, admittedly in our prototyping phases and transitioning into more of our virtual work environment. Those haven't been quite as regular, but that is part of our process that we're looking to start working with and implement those in some of our Atlassian tool suite that we're using. We do run with an integrated requirements design and test Scrum team. So we're all on the same Scrum team. We've got folks from every discipline there. We all work together. We also have had regular interface with our mission and fault management team. That team is the one that defines the flight software algorithms and does a lot of the fault management definition. We work with them regularly. And then we've also been interfacing regularly with the guidance, navigation, and control teams. So doing that early has been really beneficial to allow us to work out some kinks in the processes. It's allowed us to implement lessons learned from previous projects because we're working a launch vehicle, but it's a very different scale than some of the projects that we've worked in the past. And so we've been able to work directly with those two teams to collaborate more effectively and use this agile process to allow us to make quicker changes to adapt to the needs of the other teams. And then we've also been able to leverage the work that team members working other projects are doing if there's overlap. One good example of that is that there was another team conducting a trade study on static analysis tools. We weren't quite there yet, but they asked for some support from team members that were working in a Linux environment. And so we've got team members supporting them. They're able to assess those tools for the other project, but also try to do some early runs of those tools on our MAV prototype code so that we can support those decisions when we get to that point. So we've been using this process to really focus on, iterative process improvements since day one. Next slide. On more the development side, our preliminary lab setup, again, on the Marshall Technology Innovation Project, we started about 2 years ago. Our first setup there was that we were running a GR712 Leon 3 development board. And we didn't really have any prototype code. We didn't have a lot of ground rules and assumptions. So we worked with what we knew. So we got RTEMS running on that board. We got CFS running on that board. And we had some applications that we developed for Lunar Catalyst and other in-house CFS software testbed projects. And so we got that running on the development board so that we could gain additional familiarity with the platform, with the operating system, and with the CFS framework. So we leaned forward there. We were working with an IMU sensor and at the time a star tracker sensor, and did some assessment, really just on paper of the ICDs that we were seeing for potential hardware choices for MAV and the hardware we had in-house. Next slide, please. our current lab configuration, we have a Sphinx prototype board, which is a JPL developed single board computer that is running the RTEMS operating system. It's running Core Flight System. And then we have some Notional MAV, IMU, and navigation applications, as well as some prototype guidance, navigation, and control code. We were able to conduct performance testing of that prototype code, and that's allowed us to help work with the GNC team to drive some algorithm optimizations and also help define the hardware requirements. You know, early on, sometimes hard to define the requirements for a flight computer when you have no idea, you know, how big the code is going to be at the very beginning. And so this has given us some really concrete data on how we can drive out those requirements. So you'll see the image of the Sphinx board with a notional IMU that we had in the lab that we were able to work with there. We do also have some additional applications that we've developed based on ground rules and assumptions that we've got running as well. Next slide. And again, this is our current flight software prototype that'll show you kind of just the software side of what you're seeing in the previous slide. We've got RTEMS running. We have the scheduler, CITO, the ability to do CFDP, and then we've got a nav app all running with an IMU app. We can run that with the IMU hardware or an emulator. And then we have the guidance and control code from the GNC team over in another branch that produces that information with a Newtonian physics simulation. That outputs the data to a CSV file, and then we have a homegrown visualizer that we call the MAVViz 3D, where we can see the results and see if we would be able to successfully deliver the Oz to the correct orbit based on our current flight software. And so, and you know, for being at phase A and not at SRR yet, we feel like we built up a pretty significant flight software capability, and we're able to integrate new drops of GNC very easily and see how those perform. And we're able to add new apps very easily. Next slide. One of the areas that we focused this risk reduction on is that we have been able to have a brass board flight computer in-house since the very beginning. So while we've had to do a lot of our development and testing using emulators while we've been off-site, before we went on to telework, and then subsequently with some approval to do some on-site work, we've been able to use those brass boards to conduct some real high-level functional unit testing on the prototype code. And we can drive out a lot of the problems here with less impact to cost and schedule. I think there are already some significant things that we've looked at in terms of both performance on the flight computer and, you know, just interaction between, you know, getting the GNC code from another group and how that integrates into the CFS framework. I think we've all been able to really increase our understanding of how that works, as well as drive out some of the potential problems. And of course, you know, this is kind of the classic curve of as your program cost schedule increases, as your test venue fidelity increases, and as your as you get farther in the project life cycle. So we're hoping that this early prototyping will really help us drive out a lot of issues to avoid issues down the line. Next slide, please. So just kind of a summary of the things that we've seen through our early development. We've been able to participate in conceptual design studies and early trade studies, and the team was really able to experience the whole project formulation phase of a project at NASA. So we were really able to understand some of the multidisciplinary considerations that come up during pre-phase A. I know for me personally, and I think the team would echo this as well, that was a very unique experience because we were able to sit, you know, around the table with all the different disciplines. And sometimes when you're focused on software development, you know, your focus is there and you don't get to understand why some of the architectural decisions were made the way they were early on. So I think that was very valuable for everyone to see that phase of a project. We were also able to assess the software impacts of the various architecture changes early on. we were going through several vehicle iterations very early, and we could look at each one of those and say, hey, this is how it'll affect the software. And I think that was value added to the project as a whole. We've been able to use our Agile Scrum process to support the incremental buildup of capability, and we can address immediate concerns. So if we see something that doesn't look quite right, we can adjust as we go, and hopefully by the time that we're into really serious release cycles, we'll have a lot of those kinks with our process worked out. We've been able to identify potential hardware constraints and assist with hardware requirement definition. And then also provide some hard data on the performance of the software on the hardware that's under consideration for the mission, because that's still an open trade space at the moment for several of those components. We've also been able to identify areas where we're really going to have to watch, optimization for our flight software. Some of the more computationally intensive processes, we've been able to identify those and kind of highlight where we're going to have to focus those efforts in the future. And I think one of the major benefits we've seen is that early and effective collaboration with the GNC and M&FM teams. I think that's something that we really have strived to make seamless. I don't think that's been an issue in the past, but I think we've implemented some unique ways there to collaborate with them, just almost on the spot, so they can, we can tell them, hey, we're seeing this, and they can send us a change, and we can iterate, run it on the hardware or even on the emulator while we're teleworking, and see what the effect of that was. And then support the hardware procurement need dates and decisions. So we feel like our involvement early in the process has allowed us to have both process and technical improvements going into MAV Phase A. We've really enjoyed the opportunity, like I said, to experience project formulation and see a project from the very beginning, see how things evolve. And so we feel like that's been a unique opportunity that we hope will serve us well in the future. So, and with that, I will open it up for any questions that we may have.
Excellent. Thanks, Stefanie. First
No
question from Alexandra Holloway. Which static analysis tools did you select for MAV?
So we have not actually made a selection just yet. Some of the ones I believe that were under consideration, we were looking at Code Sonar, and we were looking at Parasoft. I think there were maybe a couple others they looked at, and I don't recall all of those, but those were the two that we've looked at most recently. I would expect we'll make a decision in the next 3 or 4 months on that.
Okay. Next question from Taylor Whitaker. About how large is your software development team on MAV?
So we've actually about tripled in size over the last 6 months. Last year we had just 3 of us, actually myself included, and we've recently added, we've got, let's see, 5 developers now, not all full-time, but some half-time, so about probably a total of 4 people full-time. And we have a requirements person and a process CM person.
Okay, next question from Ted. What role is system simulation going to play in the software development process?
So I'm glad that he asked that. We actually have a presentation on Thursday by a couple of my team, my developers on my team, Derek and Jason, and they will be presenting about their CFS-based simulation that they've been working with early on. And then we're also looking at some additional hardware in the loop frameworks that we may look at later on. But that's kind of where we are right now. We know that's a critical piece, and we're actually doing a trade study right now to look at those options.
Okay, great. Next question from Guillermo. How does the MAV return samples to Earth? Does it rendezvous with another vehicle that's in Mars orbit? If that's the case, are you planning to use vision-based navigation for that?
Yes, so the MAV actually releases the samples into the Martian orbit. And there's an Earth return orbiter, and that project is managed out of ESA. And so there will be a rendezvous with the ERO and the orbiting sample. I believe Goddard may be working that as well. I'm not personally real clear on all of the specifics about how that rendezvous happens, but that's the general.
Great. Another question from Nicolo. Are other teams, including non-software teams, adopting Agile too? And how do you stay synchronized with those teams? And how do you manage dependencies?
So I would say that as a whole, we typically it's the software team that is using the Agile process. I know we have talked about how to implement that on the hardware side as well. So I think that's been slow going. I would say for me personally, I think that's a good goal to have, and I think there could be some real benefits to that. I think with like the GMC team, for instance, they don't do a formal Agile process like we do, but I think they kind of do something similar with iterations, and that's been really helpful that we've been able to sync up with them, you know, on a regular basis, like a 2-week cycle.
Okay, maybe time for one other question from Greg with respect to MAV software development. How has software assurance played a role in the program oversight and support, if any?
Sure. So, you know, as I said, we're just getting started in phase A. So to this point, we've been doing a lot of prototyping, but I do have, you know, fairly regular meetings with our software assurance folks. And so they will be, you know, they're coming on board and they will be very involved in the software.
All right, excellent. Thank you very much, Stefanie. Really appreciate it. Excellent talk.